We're going to look at the minimum cost flow problem. To begin, we define an uncapacitated network. It's a triple G, B, C, where G is a digraph. We assume that the node set consists of V1 up to Vn, and the arc set consists of E1 up to Em, and we assume that n is at least 1 and m is non-negative. B is a real vector with n entries, and C is a vector with m entries. And we assume that G is connected. And from now on, we'll simply call an uncapacitated network a network. We can interpret a network as follows. Imagine that amounts of material move along the arcs in the direction of the arcs. The entries of B denote the supplies of material at the nodes. For the node Vi, if Bi is positive, we call that node a source. If Bi is negative, we call it a sink. And if Bi is 0, we call that node an intermediate node. And the entries of C denote the cost per unit of material moving along the corresponding arcs. Here, we have a digraph, and the entries next to the nodes are the B values. So the C values are not specified here. We call an M vector X a flow if it satisfies the following constraints. So for each node, we're going to have one of these constraints, and it says the following. The sum of the entries of X that correspond to the arcs coming out of Vi minus the sum of the values of the entries of X corresponding to the arcs going into Vi is equal to Bi. And intuitively, this means that the net flow out of node Vi must equal the amount of supply at node Vi. Here we are not assuming that X is non-negative, but if it is so, we call X a feasible flow. These constraints are called flow conservation constraints. And the cost of a flow is given by C transpose X. So the minimum cost flow problem is to find a feasible flow of minimum cost. And we often assume that the sum of these supply values is 0 because otherwise no flow can possibly exist. The reason is that if you add up all these flow conservation constraints, you end up with 0 on the left-hand side and the sum of the Bi values on the right-hand side. So the sum of the Bi values must be 0 if you want to have a flow. Note that this condition is only necessary and not sufficient. It is possible that this is satisfied and we still don't have a feasible flow. So the minimum cost flow problem is really a linear programming problem, and we can write it as minimize C transpose X subject to Ax equal to B, x greater than equal to 0 for some matrix A. And this matrix A is the node arc incidence matrix of the digraph. So the matrix A has to be such that Ax equal to B give us all the flow conservation constraints. And the way to define the node arc incidence matrix is as follows. The ij entry of A is 1 if Vi is the tail of the arc Ej, -1 if Vi is the head of the arc Ej, and 0 otherwise. That means that each row corresponds to each node, and each column corresponds to each arc. So let's work out the node arc incidence matrix of this example here. So we have 4 nodes and 5 arcs. That means A is going to be a 4 by 5 matrix. The first column corresponds to the arc E1. And since V1 is tail and V2 is head, the first column will be 1, -1, 0, 0. Let's move to the arc E2. It has tail V2 and head V1. So the entries in the second column will be -1, 1, 0, 0. And we move to the arc E3. It has tail V2 and head V4. So the entries in the third column will be 0, 1, 0, -1. And we can fill in the rest. And this is our node arc incidence matrix. As you might notice, every column of A has exactly two non-zero entries, 1, 1 and 1, negative 1. And that's because every arc has exactly one tail and one head. And so if you add up all the rows of A, you'll get a row of zeros. And that means the rows of A are not linearly independent. But under the assumption that G is connected, we can take any n- rows of A and they will be linearly independent. This leads to the notion of a truncated node arc incidence matrix. And we denote that by A tilde. And we'll define it to be the submatrix of A containing only the first n-1 rows. And we'll also define B tilde to be B1 up to B n-1. We can reformulate the minimum cost flow problem as minimize C transpose X subject to A tilde X equals B tilde X greater than or equal to 0. And this is a linear programming problem in standard form. Since A tilde has full row rank, we can apply the simplex method to this. But because of the special structure of A, the simplex method can actually be specialized to what is called the network simplex method. And in order to exploit the special structure, let's look at what is known as a tree solution. So let T be a tree in G with n-1 arcs. The tree solution determined by T is a flow X star such that the entries of X star corresponding to arcs that are not in T are 0. So let's look at an example. Say we consider the tree consisting of the arcs E1, E3, and E4. So E1, E3, and E4. So the arcs E2 and E5 will have to have value 0. And that means in order to satisfy the flow conservation constraint at node V3, the value on E4 must be 1. Because remember the interpretation of the flow conservation constraint, the net flow out of a node has to equal the supply value at that node. Because there's no flow coming out of V3, we must have 1 unit of flow going into V3. And that's only possible if we set the flow value on E4 to 1. Once we have that, we see that E3 must have flow value 3. And we can now finish off by setting the flow value on the arc E1 to 3 as well. So here, the tree solution determined by this tree is 3, 0, 3, 1, 0. Let's look at another tree. This time we're going to consider E1, E3, and E5. If we look at the node V4, we get that the flow value on the arc E3 must be 2. And so the flow value on the arc E1 must also be 2. The flow values on E2 and E4 are 0 because they are not in the tree. But now E5 has to have flow value negative 1. So this is a tree solution determined by the tree with arcs E1, E3, and E5. It's a flow, but it's not a feasible flow. So if a tree determines a feasible flow, we call the tree solution a feasible tree solution. So in this case, this is not a feasible tree solution, where this is a feasible tree solution. Why are we interested in tree solutions? It's because of the following. X star is a basic solution to A tilde X equals B tilde if and only if it is a tree solution. And so basic solutions and basic feasible solutions correspond precisely to tree solutions and feasible tree solutions. And when we look at the network simplex method, instead of working with basic solutions, we'll be working with tree solutions. And this is where the simplification comes in.